So, today we are going to discuss kinetic stability or thermodynamic stability. We have two terms we have to discuss: kinetic stability and I can say thermodynamic stability. Remember, okay? So, let's say I have an let's suppose the entropy is positive. Okay, the total entropy is positive. So, what does it mean? That the reaction is feasible. The reaction is feasible. But still the reaction is feasible, but to start that reaction, activation energy is very high. To start that reaction, activation energy is very high. So I can say that it is kinetically stable. Remember. So what is kinetic stability? Kinetic kinetic stability. What is kinetic stability? What is kinetic stability? So when the activation energy is very high, when the activation energy is very high, okay? So the reaction will not take place at room temperature. Of course, the reaction will not take place at room temperature. The reaction will not take place at room temperature since the activation energy is very high. So we can say that, so we can say reaction is kinetically stable. Reaction is kinetically stable. Then we have thermodynamic stability. Thermodynamic stability. So thermodynamic stability means that uh, basically it depends. And when the reaction is kinetically stable, so what does it mean when the reaction is kinetically stable? So it depends on the rate. It depends on the rate of reaction. It depends on the rate of reaction. Entropy, i- the term entropy is irrelevant to describe kinetically stable reaction. Entropy is something else and kinetic stability is something else. There is no relation between the entropy and the kinetic stability. It's all about the activation energy. If the activation energy is lower, so the reaction can start easily, means that the reactant can react easily. And if the reactant can react easily, I would say that they are going to be unstable, isn't it? I would say that this is unstable. But but if we are looking at thermodynamic stability, so it depends on the entropy. Remember. So I'm telling you the relation between the entropy and these two terms. Examiner would be asking, it's in your syllabus. So thermodynamic stability means that it's entropy dependent. It's entropy dependent. So if the overall entropy is positive, so the reaction would be spontaneous. If the entropy is positive, if the entropy is positive, so remember, Uh, the reaction would be spontaneous. Reaction is spontaneous. So, what do you mean by this? I can say the reaction is thermodynamically stable. The reaction is thermodynamically stable. Okay. The reaction is the reaction is thermodynamically thermodynamically stable. The reaction is thermodynamically stable. So they will be asking these two terms. And also we have a relation that's called the relation between the delta S and the rate constant. We have the relationship between entropy and K. K means constant. What's the relation? The relation is delta S is equal to R ln K. R ln K. Okay, that's the relation. And this entropy means it's the total entropy change. This delta S means it's the total entropy. Okay, total entropy means that system plus surrounding. Total entropy means that system plus surrounding. So I can say, or this can be written as delta S of system plus delta S of surrounding is equal to R ln K. And we know that the formula for the delta S of system would be sum of the entropies of the product minus sum of the entropies of the reactant side. This is system. And then I have surrounding. Negative delta H over T is equal to what? R ln K is equal to what? R ln K. Remember. So this K is, it's a constant. This K means it's a constant. So you need to know this relation. That is equal to R ln K. In most of the MCQs, they will be asking, like we were doing the paper in the last class. In that paper, they were asking about the R ln K. Let me show you that paper. Let me show you that paper. Wait. Let me show you that paper. It was, I think, 2025 paper. Wait. 2025 paper. Unit 4. 2020. I'm again sharing. Wait. 2025 May, or yes, this is the question paper. I'm going to share my screen. And also, before discussing that, we need to know what is Gibbs free energy. We need to know what is Gibbs free energy. What is Gibbs free energy? Gibbs free energy is represented by delta G, represented by delta G. Okay, so delta G is equal to delta H minus T delta S. That's the relation. So, I was saying to you that initially when the reaction used to be exothermic, so we used to say that this is going to be spontaneous, and if the reaction is endothermic, so the reaction is non-spontaneous. But the enthalpy change was not giving us the full-fledged information regarding the spontaneity of reaction. Then we have introduced the term entropy. And then after discussing entropy, I told you that if the total entropy is positive, so the reaction is spontaneous. And if the total entropy is negative, so the reaction is non-spontaneous. So then again, I can say We have some cases in which the entropy change is positive, but the reaction is non-spontaneous, and vice versa. So we are supposed to have strong relation, you know. So after using that relation, I can decide the spontaneity of reaction. So that's one and only that is called Gibbs free energy. Gibbs free energy is the relationship between all the terms. It has enthalpy change, it has a temperature, it has entropy change. So it's the relationship between these three. So after discussing these three factors, finally we can tell the spontaneity of reaction, whether it's spontaneous or non-spontaneous. So I can say that this is enthalpy change. It should be in this is enthalpy change, which should be in kilojoules, kilojoules per mole. And this is your temperature. It should be in Kelvin. It should be in Kelvin. And this is the entropy change. And you know what's the unit for entropy? Joules per mole and then per Kelvin, right? So uh, if the overall delta G is negative, if the overall delta G is negative, so you know, if the delta G is negative, so I would say that the reaction would be spontaneous. The reaction would be spontaneous. And if the overall Gibbs free energy, that is delta G, is equal to positive, if delta G is equal to positive. So positive means that the reaction is non-spontaneous. The reaction is non-spontaneous. Like in entropy, what was the relation? If the entropy was positive, so the reaction was spontaneous. But right now I'm saying if the delta G is positive, so the reaction is non-spontaneous. So we will have to calculate the delta G. Okay, for delta G, what should be given? Delta H, also the temperature, and also the like the delta S. After putting the values in this, so I would say that the reaction is spontaneous or like non-spontaneous. So see this question, this is section C, paper 2025. It's May unit 4. So what they are asking in this question, see this one. Uh, yes, they have given you the table, okay, also the equation. And first of all, they are asking to calculate the standard enthalpy change for this reaction. And you know, what's the formula to calculate the enthalpy change? It's product minus reactant. Can you tell me the answer for enthalpy change? Answer for enthalpy change.
Sir, is it minus 1222.4?
Minus minus one, minus one. Okay, okay, that's the answer for entropy, sorry, delta H. And then what you have to do, you can see they're asking to calculate the entropy as well. Entropy of the system. And you know, what's the formula for the system? It's product minus reactant. Again, what's the answer for entropy change? The answer for the delta H is the answer for the delta H is 79. If you're getting the same, so that's good. Yes. What's the answer for entropy? Equation is given, the same equation. It should be 160. Are you getting the same answer? 160. Okay, good. And now see this question. In this question, what they are asking, using your answers from A part 1 and A part 2 to calculate the lowest temperature at which hydrated copper sulfate will decompose. Okay, so using part A and part 2. In part A, we got the answer for enthalpy change, and in part 2, we got the answer for entropy change. And we have the relation that is delta G is equal to delta H minus T delta S. Okay, so temperature is unknown, delta H is known, delta S is known, and what about delta G? What about delta G? So you will be taking delta G is 0. You will be taking delta G is 0. Okay. Then after taking it 0, then you can easily find out the temperature. You can easily find out the temperature. Of course, all of the things are known and the temperature is unknown. It's of 3 marks. You can calculate it very easily. So I'm going to tell you the answer you can match. The answer is 500 Kelvin, around 500.9 Kelvin. Are you getting the same answer? 500.9 Kelvin. After using the relation delta G is equal to delta H minus T delta S. So T is unknown, enthalpy change is unknown, entropy change is, sorry, enthalpy change is known, entropy change is known, delta G is equal to 0. Then you can do the temperature. Are you getting 500?
Sir, I got 0.500, not 500.
50 what?
0.500.
Ah, okay. You know what? You did the mistake. I told you that the unit for enthalpy change is kilojoules per mole, and the unit for delta S is joules per mole per Kelvin. So you are supposed to convert the unit of entropy from joules to kilojoules after dividing by 1000. Then you would be getting the same answer.
Sir, can you repeat, please?
The unit for the entropy change is joules per mole, isn't it? And the unit for
Yeah.
the enthalpy change is kilojoules per mole. So the unit should be the same. So what you have to do, you have to convert Entropy from joule to kilojoule. Okay. Now see this question. Yes, what's the answer for this question? Hmm? Which of these substances would be expected to have the greatest standard molar entropy? Yes,
D. D.
D.
Because it has
Uh,
more, most of the, like more atoms. Yeah.
exactly. More atoms means more randomness. Okay. Okay, the answer D is correct, right? And afterwards, yeah, that's it for this paper. Okay. And let me take another paper of January 2025. Again, we would see the same questions related to entropy and about the temperature. So the thing is, whenever he would be asking to calculate the Gibbs free energy, so he has to give some other values as well. I'm talking about delta H, delta S, and also the temperature that should be in Kelvin. Sometime he would be giving you the temperature in degree Celsius. So you have to convert that temperature into Kelvin after addition of 273. Okay. So see this one. Yes. Okay. Okay. Yeah. See this question. Which pair of values will always give a thermodynamically feasible reaction? Entropy change of the system, enthalpy change of reaction. Entropy change of the system. So entropy change of the system should be positive, isn't it, for a thermodynamically feasible reaction? As I told you, if the overall entropy is positive, so the reaction should be so the entropy should be positive and the reaction should be spontaneous. So C or D may be correct because in C or D the entropy change of the system is positive. Okay, so the reaction should be thermodynamically feasible reaction. And what about the enthalpy change of the reaction? Okay, so thermodynamically feasible reaction means that, you know, it should be negative. Like exothermic reactions are thermodynamically feasible reactions. You know why? You know why? Because for exothermic reactions, the products have a lower energy, isn't it? The products have a lower energy. Why the products have a lower energy? Because they have released energy from the system to the surrounding. So now they have a lower energy. I'm talking about the product side. So if the product side is going to have a lower energy, okay, So means that the reaction is thermodynamically feasible reaction. So yes, the answer is C. So yes, the answer is C. Okay. And what about this one? Hmm? Again, the same concept. Again, the same concept. Liquid is wrong because in a liquid, the randomness is lower and in a gases, the randomness is higher. So then we have to see the total number of atoms. So it should be NO2 means D for doctor is correct as the previous paper. And okay. And see this one, they are going to ask the entropy change of the surrounding. Entropy change of the surrounding. So we know the formula for the entropy change of the surrounding. No, they are asking the enthalpy change and they have given you the entropy of the surrounding. And of course, we know the formula that is delta S is equal to minus delta H upon T. Okay, minus delta H upon T. So I would say that the value is negative, then you can calculate the value easily. What's the answer for this? And by the way, you have to convert the temperature into Kelvin. 25 plus 273 would be equal to 298 Kelvin. Yes. What's the answer? Fast. Mhm.
Minus 70.
Minus 70. Minus 70, minus 70, minus 70, minus 70. Okay. Uh, Let me check the marking scheme. It's question number 19. Okay. So you are saying minus 70.
It's positive, not minus.
Okay. The answer is positive 70. Okay, good. Good. The answer is positive 70. Right. And what would you say about this reaction? Question 19. Yes. Many effervescent products, such as vitamin tablets, are solids which contain citric acid and sodium hydrogen carbonate. Only when these tablets are added to water is fizzing observed. The equation for the reaction is shown. Give two reasons why this reaction is thermodynamically feasible when considering the entropy of the system. So you can see it's changing from solid to gas. In the product side, you have different products in which one of the product is a gas, isn't it? So I can say the entropy is going to increase because the randomness is going to increase because we have the solid particles, they are going to convert into the gaseous particles. So randomness is increasing due to the presence of a gas. Okay. And also the number of products are increasing. In the reactant side, I have how many moles? 3 plus 1, 4 moles. And in the product side, I have 3 plus 3 plus 1. So total we have 7 moles of the product. So yes, when the number of moles are increasing, so means that the reaction is going to be more spontaneous. Like it's thermodynamically feasible. That's why. Okay. So that's all about the, I can say, entropy. And then, uh, so now you must know what's the difference between, like, what's the relationship between the thermodynamically stable and also like the entropy. Okay. Okay, then we have this one. Then we have this paper. You can see this one. Okay, yeah. See this? They are asking about the entropy. Hopefully you will do this question. It's a baby question. Okay. So 2 marks. I'm leaving this question. Okay. Answer. Product minus reactant. Again. Okay. Or entropy change of the system. And okay. So in this paper, what's that? It's October 2024. In this paper, this is the only one question related to entropy. Wow. Okay. Okay. Yeah. Then we have this paper. This is wait. Uh okay. Yeah, that's the paper. Yes, good. Then we have May 2024 paper. May 2024 paper. You can see this. You can see this paper. Yeah. Yeah. Question number 5. Yes. So what would you say about this question? Hmm. Question number 5. For all chemical reactions, let me tell you the marking scheme as well. First, you have to do this question. Okay. Yeah. Think about this, and then I'm going to show you the marking scheme. Equilibrium constant, that is K, is related to the total, as I told you this relation, right? By the expression shown. So the S total for a reaction is negative, right? Which statement is true. The value of K is less than 1, the value of K is greater than 1, the value of K is negative, and the position of equilibrium lies to the right. ln ln is a log. It's not log base 10. No, it's another log. It's natural log. The base is not 10 for this one, okay? And also, when the entropy change is positive, so what does it mean? The entropy is going to, like, when the entropy is positive, so means that the reaction is feasible and the more products are being formed. Means the equilibrium lies to the right. And when the entropy change is negative, so means that the reaction is non-spontaneous, so the equilibrium lies to the left because there will be more number of reactant side. Okay, because the reaction is not feasible. So after looking at this question, also they are saying that the entropy change is negative. So the value of k is less than 1. So if I'm going to take the if I'm going to take the ln of less than 1, let's say if this is going to be 0 0.6, 0 0.5, and in the B option they are saying the value of k is greater than 1, let's say if I'm going to take 1.5, 1.6, 1.7, so am I getting the negative delta g or not? Then if I'm going to take the ln 0, k is like, sorry, negative 1, negative 1.0, negative 1.6, negative 0.6. Okay, so am I getting the negative delta s? Yes or no? Or then in option D, they are going to say position of equilibrium lies to the right. So you can see in this question, they are saying the answer is A. So you can uh, you can confirm this by taking the value in your calculator and then just take negative like ln. So are you getting the negative answer? See this? If yes, so that's why this answer is correct. Yes. Let's say, just take 0.6, 0.4, 0.2, 0.1. So are you getting the negative answer? Hmm?
Yeah.
Okay, good. So that's why this is going to be correct answer. So you will see a lot of questions related to this. Sometime they will be using LNK, sometimes they will be asking other thing. Like in this question, they are asking the entropy of the system. This is very easy. In this question, they are going to ask the entropy change for the surrounding. Again, this is very easy. And in this question, they are going to ask about the total entropy. It's going to be the sum of system and surrounding, or yeah. So, why the entropy change of the surrounding for reaction 2? Reaction 2, what's reaction 2? Okay, in this reaction, gas is changing into the solid. Entropy is negative because randomness is decreasing, isn't it? Randomness is decreasing. So if the randomness is decreasing, so what they are asking? They're asking why the entropy change of the surrounding for reaction 2 is highly positive in terms of the bond strengths of the reactant and the product. You know, when the surrounding is highly positive, means it's endothermic. The reaction is absorbing energy. That's why the container becomes colder in an endothermic reaction. And you know, by the way, the container is your surrounding. And the container becomes hot in an exothermic reaction because container is your surrounding. So in terms of the bond strengths of the reactant and the reactants and the products, it's of only 1 mark. So what would you say about that? Yes, it's of only 1 mark. Mhm. Mhm. Yes, Iman, Manal, what do you think? Hmm? No? See this.
Not sure.
Manal, what do you think, Manal? It's 15C. See this? So now you have to do practice for the past paper because this topic is easy, but to polish this topic, you need to do some questions. So this would be very easy for you. So, uh, like, when the, like in this question, what they are asking, look at this carefully. Entropy change of the surrounding for reaction 2 is highly positive. Highly positive. So highly positive means that the reaction is endothermic. Why this is so? Reaction 2 is given. And in reaction 2, you can see these are the species. Everything is given like this is balanced chemical equation. So they are saying in the marking scheme that OH bonds are stronger than SiH bonds. OH bonds are stronger than HI bonds. And they were saying in the question the entropy change for the surrounding is positive. Entropy change for the surrounding is positive. So, if the entropy change of the surrounding is positive, so means that the randomness is higher, isn't it? The randomness is higher. That's why the entropy is positive. When the randomness is higher, when the temperature is higher, when the temperature is higher, so the kinetic energy of the particle is higher. When the kinetic energy of the particle is higher, so I can say the entropy would be higher. So what do you mean by this? The like the kinetic energy of the particles of the surrounding is higher. So I can take an idea. It means that it means that the surroundings temperature is higher. You know, it means that the surroundings temperature is higher. And when the surroundings temperature is higher, when the reaction is exothermic, okay? Container becomes container becomes hot. Container is your surrounding and the temperature of the surrounding is higher. They are saying the entropy of the surrounding is very positive. So they are not telling us directly. They are telling indirectly in terms of entropy. They are saying entropy change is positive. So we know that when the entropy change is positive, when the temperature is higher. So why the temperature is higher? Because it's going to release energy. That's why. So overall reaction is exothermic. And when the overall reaction is exothermic, we know the two definitions. Number one, on the basis of bond energy. Another one, it's a general definition. The reaction in which energy is released. And what about the endothermic reaction? The reaction in which energy is absorbed. That's the general definition of exothermic and endothermic. And what are the definitions on the basis of bond energy? So if you have ever listened about that, more energy is released than absorbed. More energy is released than absorbed. So this is going to be exothermic. Okay. And what about endothermic? More energy is absorbed then released. It's going to be endothermic. These are the definitions of exo and endo on the basis of bond energy. So, yes, they have written OH bonds are stronger than SiH. What do you mean by this? Let me show you the paper. So after this question, when you will see the same question, so that would be very easy for you, right? So now you can see OH bonds in water. In water, I have OH bonds, and in SiH4, I have SiH bonds. So it's easy to break down the SiH bonds. So less energy is absorbed, and it's difficult to make the OH bonds because it's very stronger. So more energy is like I can say in the product side, the bonds are being formed, and in the reactant side, the bonds are being broken down. So less energy is required to break down the bond, and more energy is released when OH bonds are formed. So that's why this reaction is releasing energy. Therefore, the temperature of the surrounding increases. And that's why they are saying entropy change for the system is positive, surrounding is positive. You know, it's indirect question. So you need to know the terms, what the examiner is using. It's of only 1 mark. See this question, why the entropy change of the surrounding for reaction 2 is highly positive? You know what they are asking. Manal, are you getting my point? Iman, yes?
Yeah,
Yes, sir.
kind of.
Okay. And what about this one? Uh, yes.
Sir, can you scroll up?
Sir, is it A?
Which of these statements is true? A means the enthalpy change of formation of lead nitrate is minus 2151. Like, did you calculate the enthalpy change? Oh, okay. Let me see the marking scene. I didn't calculate this one. So this is question number. This is question number three. Yeah, okay. So question number three says it's going to be C. Like, did you get the same value minus 2151?
One second, sir.
And of course, this is wrong. We saw the marking scheme. So you won't be calculating this. You won't be getting this value. Then in B, the enthalpy change of solution of lead nitrate is exothermic. We can't say about the solution, We can't say about the solution because it may be exo, it may be endo. But they have given us the values for the hydration and also the lattice energy. So we are getting the positive answer. So option B is incorrect because it's endothermic. And in C, they are saying enthalpy change of hydration of a lead 2 ion. Lead 2 Pb2 plus ion is more exothermic than that of a nitrate. Nitrate is NO3 minus. Nitrate is NO3 minus. It's a negative ion. You know what's the enthalpy change of hydration? Hydration means when water is going to surround the ions. It may be cation, it may be anion, right? By the way, it's it's general observation that it's a general observation that like the size of the cation is lower than the size of the anion. Anions are larger, cations are smaller. When the size of the cation is smaller, when the size of a cation is smaller, so the hydration would be more exothermic because more energy would be released. Because more energy would be released. So that's why the answer is C. Okay. So that's why the answer is C. Okay. So these are the questions related to entropy. Now you have to do practice for by yourself, and then that's all finally for this chapter. Then we would be starting the next chapter. Okay.